Testing, testing, 1, 2. Hi, this is Orijuela. I am your instructor for CSE4010, Contemporary Computer Architecture, and this is the accompanying video for Lab3. So over here is in front of me I have the lab. But before we get into it, let's talk about the material that you need to know in order to do this lab. So preferably you shouldn't do this lab until you've already covered chapter 3 material. Over here I talk about addition and subtraction. So at this point you already know how addition and subtraction is done by hand, but one thing that you need to know is how addition and subtraction is done using computers. So as you already know, addition and subtraction is done using binary, where in this example here, let's say that we wanted to add 6 and 7 in decimal and then add it together using in binary. So the way we do that is that we convert 6 to its binary form by representing it as 0, 1, 1, 0, and then we represent 7 in binary by changing it to 0, 1, 1, 1. And then if we wanted to add, well, in this example we're subtracting, but addition and subtraction is the same thing. They're just inverse processes. If we wanted to add, we would just do it in binary. But in this lab here, we would like to know what's the underlying circuitry that allows this to happen. So the way that actually happens is using half and full adders and half and full subtractors. So I'm going to show you this PowerPoint here, and let's look at it together. Okay, so here is a little reminder of here are a list of some common decimal values. It's binary representation, decimal values, and its binary representation. Okay. To perform addition of large numbers, it is important to construct a circuit that can handle the addition of simple numbers. Okay. If we can create a circuit that handles the addition of simple numbers, then we can use several of these to construct a circuit for adding large numbers. Okay. So to do this, we use something called I should move my head out of the way. So to do this, we use a circuit called a half adder, and you're going to see the reason why it's called a half adder in a second. But a half adder is probably the most simple circuit you could make that can represent addition. So in the previous lab, you learned all about the different types of gates, right? We have the AND gate, OR gates, NOT gates, so on and so forth. Well, it looks like we're going to be using these gates in order to construct our half adder. So before we even construct a circuit, let's ask ourselves how exactly we want this circuit to work. Okay, so we've been making circuits in Verilog already. You've made a very simple circuit in lab 1. If you remember before, you made a circuit that takes one input A and then gives out two outputs B and C. And then you also made another circuit in lab 1 that takes two inputs W, X, and gives two outputs called Y and Z, that kind of thing. Well, let's ask ourselves, what is the behavior that we want to create with this half adder? So obviously we want to make a circuit, right? Something like this. We want to give it two inputs. Those inputs being the two variables that we want to add. As you remember, a wire can contain a charge represented by 1 or no charge represented by 0, right? So there's going to be two inputs, one called A and one called B. So this input A could have a value of 0 or 1. and this input B can also have a 0 or 1. So this is going to be our circuit. It's going to have two outputs, one called a sum. Let me move this over here. And another one that we're going to call a carry, okay? Now, it would be helpful if we drew a truth table like this one here to represent how exactly this is going to work. So, obviously, when A and B is equal to 0, if we add 0 and 0 together, we will get a sum of 0 and a carry of 0, right? If A was 0 but B was 1, we want the sum to be 1. And then when we add 0 and 1 together, there's no carry involved. So we want the carry bit to be 0. Okay. Now, if A was 1 and B was 0, if we add 1 and 0 together, it would result in a sum of 1, and then there would be no carry, right? So we want the result to be 1, and then the carry to be 0. And then the only time we would have a carry here is if A and B were both 1, right? What would happen as a result of this is that the sum would be 0, and then this carry bit would carry over to the next half adder, which would result in a carry of 1, okay? So consider the truth table for the half adder. Let's try to construct a circuit that takes two inputs that are both binary numbers A and B, and gives two outputs, sum and carry, which we did. How can we construct the simpler circuits to achieve the desired results? Okay, well, let's take a look here. So we have looking at only sum here, and our two inputs A and B. What does this behavior represent to you? So it looks like we want sum to be equal to 0 if A and B are 0. We want it to be equal to 1 if A or B was 1, but not both of them. If A and B were both 1, we would want the sum to be 0. So this looks to me like this sum output would take the exclusive OR of A and B, right? So do you remember back in Lab 2 how the way that exclusive OR works? So exclusive OR returns a 1 if either A or B were equal to 1, but not both, okay? So that's the reason why in this circuit here, we have A and B. A and B both feed into this gate here, which is an XOR gate. And the output of this would be sum, okay? So that covers the sum portion of this half adder, but we also need to come up with some way of creating the behavior for the carry, okay? So it looks like carry is only equal to 1 if A or B are both 1s, okay? So considering the behavior of A and B resulting in the carry, how are we going to get the behavior that we intend out of this? So that whenever A is 1 and B is 1, carry is 1, but any other combination result in 0. It looks like the only way we can do that is using an AND gate, like we see here. So if you recall before, this is an AND gate. And we take A over here, we AND it with B, and it results in this output here, okay? So that's how we're going to do it. So, if you're going to be using Verilog a lot, which you're going to in this course, so one thing that might be helpful for you to know is to know the difference between the unabstracted and the abstracted versions of the half adder. So let me erase all these. So this is the unabstracted version. So this shows you the underlying circuitry that's in this circuit, and this is the abstracted circuit where all of the complex circuitry is represented using this dark rectangle here. Okay. All right. So let's move on to the next slide. So what I just showed you before is actually a half adder. So the way that the half adder works is that it takes care of the addition of two binary numbers. But as you're going to see here, something that we can do with the half adder circuit is that we could take two of them together and create something that's more useful to us, something called a full adder. Okay, so over here is a abstracted version of a full adder. So it's actually constructed by putting two half adders together, but I'm about to go into that in a second. So let's read this here. A full adder is an adder which takes three inputs and produces two outputs. The first two inputs are A and B, and the third input is a C in, which stands for carry in. Okay, so the C in, you might be wondering where this C in comes from. This third input, C in, would be the result of the carry bit of the adder preceding it, if there is one. Okay, so the output of carry is designated as C out, and the output sum is designated as S, as you can see here. And over here, this is the truth table for the full adder. We'll be looking at that in a second. And then if you wanted to know how a full adder is created, the way it works is that we take two half adders and put it together. So here's one half adder here. As you can see, it takes two inputs, A and B. And then what happens is this carry gets fed into this OR gate here, okay? This is an OR gate, okay? And then the sum output of this half adder, let's just call this first half adder U1, because that's what we've been naming our circuits, okay? So the sum of this half adder is going to feed into the B input for the second half adder, which I guess we'll just call U2. Okay, and then our third input, which is our C in, our carry in, is going to be fed as the first input for U2. Okay, now what happens is the sum of the second half adder is going to be the first outputs. Okay. And then the carry output is going to be fed as the second input for the OR gate. So what happens as a result is that if I were to abstract this right now, if this is our carry in, if I was to abstract this, I would represent all of this with one big rectangle. And as you can see, a full adder takes three inputs, 1, 2, 3, and that's two outputs, 1, 2. Okay, so this is the abstracted version. And over here is the unabstracted version. So the unabstracted version, okay, actually let me, so the unabstracted version shows all the underlying circuitry. So what you see here is that this XOR gate belongs to one of the half adders, and this XOR gate belongs to the other half adder. These two AND gates belong to one half adder, and this AND gate belongs to another half adder. So I think the way that this is working, this represents one half adder, and this here represents another half adder. Now this is unabstracted, so it kind of looks like this. And then lastly, we have an OR gate to put it all together. Okay, so by creating a half adder, which is a simplified circuit, and using that to create a full adder, what happens as a result of this is that we can take multiple full adders, arrange them to connect them together, and then use this as a larger circuit to create our addition, which is what one of the topics that we've been discussing in chapter 3. So let's remind ourselves how the full adder works. It takes three inputs, A, B, and this carry in, which is the result of the previous adder, if there is one, right? So the way that this works is that if A, B, and C in were all 0, if we were to add these all together, like 0, 0, 0, this would result in a sum of 0 and a carry of 0. If A, B, and C in were 0, 0, 1, this would result in a sum of 1 and then a carry of 0. We wouldn't carry unless there's two or more ones add together, right? So if A and B and C in were 0, 1, 0 respectively, the sum would be 1, and then the carry would be 0. If A, B, and C in were 0, 0, 1, 1 respectively, the sum would be 0, right? And then the carry would be 1. So to demonstrate this, like if you had if A was 0, B is 0, if B is 1, and then you had a carry from the previous circuit that which were added together, so this would result in 0 and a carry of 1, which will go to the next adder, right? If A was 0, B is 0. If A was 1, B is 0, and C is 0, this would result in a sum of 1 and 0. If we had A was 1, B is 0, and C is 1, this would result in a sum of 0 and a carry of 1. If we had A and B both being 1, and then C is 0, this would result in a sum of 0 and a carry of 1. If A, B, and C in were all 1, this would result in a sum of 1 and a carry of 1. Okay? So, in order to understand how this works, is that I put a little example here demonstrating how it works. So, for the sake of example, let's say that we want to perform the addition of 5 and 7, okay, to make 12. Well, as you already know, computers only understand things in terms of ones and zeros. So the first thing we need to do is convert the 5 and the 7 here into their binary forms. So the binary form of 5 would be 0, 1, 0, 1, and then the binary form of 7 would be 0, 1, 1, 1, okay? So if we were to perform addition here, like this, let's perform binary addition here and see what we get. So if we have 1 and 1, this would result in a sum of 0 and a carry of 1, okay? This is where the carry comes in, okay? So like I said before, when it comes to the half adder, this carry in input would be the result of the preceding full adder if there was one, okay? So now we have a carry of 1, an A of 0, and a B of 1. So let's remind ourselves what that is. So a carry of 1, a B of 0, and a A of 0 and a B of 1. So this would result in 1. So this would result in a sum of 0 and a carry of 1, right? So as a result, the sum is 0 and the carry is 1. We have a carry of 1, an A of 1, and a B of 1. So we add these together. This will result in a sum of 1 and a carry of 1. And then we have a carry here for 1 added to an A of 0 and a B of 0. This will result in a sum of 1 and no carry at all, right? So this gives us the binary number 1100, which if you convert it back to decimal would give you the number 12, right? So what I'm trying to show you here is that because 5 and 7 were 4-bit binary numbers, we would need to use 4 full adders and connect them like this in order to perform this summation. Okay, so look in this example here. Do you see that I have a rectangle here? And then we have a output of sum, and then we also have an output of carry, right? So the way that you should visualize this is that this first number here represents A, and the second number here represents B, okay? So as a result of this, there's 2 outputs, one that's sum and one that's carry. The carry output of the previous adder feeds into the input of the next full adder, okay? So this next rectangle here also represents a full adder. It's the next full adder that comes after this one, right? So it takes 3 inputs. The inputs are this number here, which is going to be our A, this number here, which is going to be our B, and also the carry in output from the previous adder, okay? So because the first full adder resulted in a carry, this wire here would represent a 1, okay? And as a result, the summation would be 0, and then we would also have a carry bit feeding into this one. This rectangle here represents the third full adder. So it's taking 1 as A, 1 as B, and 1 as your carry in. As a result, the sum becomes 1, and then the carry goes on to the next one, and then over here is our fourth and last full adder, and it's taking an A of 0, a B of 0, and a carry of 1. That results in a sum of 1 and then a carry of 0, okay? So this is actually what we're going to code in Verilog today. So now that you know how to create a full adder and a half adder, we can go ahead and get started making this in Verilog. So let me get out of here, discard. So let me go back to the lab over here. So, have you ever wondered, added 2 plus 2 on a calculator and gave you 4 as the answer? Have you ever wondered how the calculators are able to do this? Calculators, as well as computers, only understand binary numbers, so how can a computer perform complex math? You already know the answer to that. The answer lies in its circuitry. We construct half adders and half subtractors, which are the simplest circuits we can construct for performing addition and subtraction of 2 binary bits. Then we use several of these connected together to create adders and subtractors for much larger numbers, as you saw in the PowerPoint, okay? So here, as always, I'm going to do part A for you, which is where we're going to create the half adder and the full adder, okay? And then part B, you're going to do the exact same thing, but create a half subtractor and a full subtractor, which are also given in the PowerPoint, okay? But I'm getting ahead of myself. Let's just do part A first. So, open Visual Studio Code and click the Open folder and select the Lab3A folder that you created in Lab 1. Right, so I will put this over here, and I'll put this over here. Okay. So let's open a folder. So I'm gonna go over here. You should go to the folder where you saved your labs to. So I'm gonna go here. I'm gonna choose my Lab3A folder. Yes, and here's where we're gonna get started. Okay. Okay, so hover your cursor over the Lab3A folder in the Explorer pane and click the New File button. So, New File. We're going to name this file fulladder.v. Fulladder.v. Okay. Type the following code. The accompanying video, which you're watching right now, provides an explanation. Enter comments explaining what the code does. Code with no comments gets no credit. Okay. So here's what we're going to do. The first thing we're going to do is create our first circuit, which is the half adder. So if you recall from the PowerPoints, the half adder is an intermediary circuit that we need in order to create the full adder. And the way it works is that it takes two inputs, A and B. It takes the sum. It takes an XOR gate. A and B is fed into an XOR gate, and the result of that is going to be our sum output. And then A and B is also fed into an AND gate, and the result of that is going to be our carry output. Okay. So here's what we're going to do. So we're going to say module half adder. So it's going to take two inputs, which we're going to call operand 1, operand 2, or op1 and op2 for short. And it's going to take two outputs. One of them is going to be the sum. The other one's going to be the carry. Okay. Now, we need to indicate to Verilog that op1 and op2 are inputs and sum and carry are outputs. So the way we do that is using the input and output keywords. So we're going to say input op1, comma, op2. This will indicate that operand 1 and operand 2 are inputs. Now we need our outputs. One called sum and one called carry, like that. Okay. Now, if you go back to the PowerPoint here, we need sum to be the result of the XOR of A and B. So, in case you don't know, the way that you represent XOR in Verilog is using the caret symbol. Okay. So we're gonna say assign a sum to be equal to op1 caret op2. So the caret symbol is the XOR operator. Okay. Okay, so that should take care of that. And now we need to use an AND gate to AND A and B together. So the way you do that is that we use the ampersand to represent the AND operator. Okay, so we'll say assign carry to be op1 ampersand op2. So the ampersand represents our AND operator. Okay, I'll put another comp here. Is the AND operator, and then that's it. Okay. So just like that, I now have a circuit that represents my half adder. Okay. So here is my half adder, which is created in Verilog, or which is represented in circuit diagram here. And now here's my half adder represented in Verilog code. Okay. So far so good. The next thing that I need to do is create a full adder. Okay. Now the half adder is just, the full adder is just two half adders and an OR gate fused into one. Okay. So in order to make this work, I just have to follow this diagram here. So let me grab this. Okay. I'll put this here, and then we can use this diagram to create our full adder. Okay, so here's what I'm gonna do. I'm gonna say full adder. Now I need to say module up front so that Verilog knows that this is a circuit. And now I need to list my inputs and my outputs, right? So if you recall from before, well, actually I'll use this. The full adder takes 3 inputs, one called carry in, one called A, and one called B. And has 2 outputs, one called sum and one called carry. Or carry out, as you see here. So I'm going to list my inputs and outputs. I'm going to say A, B, carry in. Those are my inputs, okay? And then my outputs are going to be sum and carry out. Like that, okay? So, as always, I need to indicate to Verilog which of these are my inputs and which of these are my outputs. So I'm going to say input A, comma B, comma carry in to let Verilog know that these are all inputs. And now I'm going to say output sum and carry out as my outputs, okay? Alright, so let's do what we need to do here. So in order to make the full adder, that's what this whole thing is. It looks like we're going to need to make a first half adder here. Let's call this first half adder U1. And it's going to take inputs A and B. And it's going to give 2 outputs as well, okay? And these 2 wires that I drew here, this one and this one, these don't have names yet, but I'll give them names later. So let's create our first half adder. So we're going to say half adder. Now we need to give this circuit a name. So I'm just going to call it U1 because I did so in this diagram. So U1. Keep in mind that these are just variable names. You could actually name this half adder anything that you want, but I just decided to call it U1 to keep it simple. So as you can see in my half adder definition, it's going to take 2 inputs and 2 outputs. So I need to indicate what they are going to be. So according to this diagram here, the 2 inputs are going to be A and B. A, comma B. And now I have 2 outputs here. This wire here and this wire here. These wires don't have names, so I'm just going to give them names. I'll call this wire C, and I'll call this wire D. Okay? So I'm going to put C, comma D here. Now, I also need to indicate to Verilog that C and D are intermediary wires. So the way I'm going to do that is I'm going to use the wire keyword, and I'm going to put C, comma D here. Okay. So this is the first half adder, okay? So that part's done. Now I need to make the second half adder, which is gonna be this one here. I'm gonna call this half adder U2. Okay? So let's say half adder. So this creates my second half adder. I'm gonna call it U2. Now I need to tell myself what are going to be the inputs and what are going to be the outputs. So for this half adder here, it takes 2 inputs. The first input is going to be my carry in input. Okay, so I'm going to put carry in here. The second input is going to be this intermediary wire, which I named C. Okay, so I'm going to put C as my next input wire. Okay. So what are my outputs going to be? Well, it looks like I'm going to have I'm going to have an output here. This is going to be my sum. So this output is a wire that has no name. So I'm just going to call this wire E. And this output wire here, it also doesn't have a name, so I'll just call it F, okay? So, because I need more wires here, I'm going to indicate to Verilog that I'm going to need 2 more intermediary wires, by putting 2 more here, they're going to be called E and F, like that. Okay. And then I'm going to indicate E and F as my outputs for the second full adder. Okay. Now I'm not done yet. Okay. So the last thing I need to do is take these inputs, these 2 wires here, the one that I called D and the one that I called F, and have them be fed into this OR gate here, okay? So here's what I'm gonna do. So since this output here, since this wire is my carry out, carry out is going to be the OR of F and D, as you can see in the circuit here, okay? So I'm going to say assign carry out to be equal to the OR of F and D. So I'm going to say the way that you indicate OR in Verilog is by using the horizontal bar. And I'm going to say D, comma. And then lastly, I need to have my sum outputs. It looks like the output for sum of the second half adder U2 is going to be equal to whatever this wire E is. Okay, so I'm going to say assign sum to be equal to E, and I'm going to say and Orijuela. Okay. So now I've completed my full adder here. Okay. So the way that I can to recap everything that we did so far, the way that I constructed my half adder was that it takes 2 inputs and 2 outputs. The 2 inputs are A and B. The output is sum and carry. Sum is the XOR of A and B. Carry is the AND of A and B, okay? After that, I used 2 half adders and an OR gate to create a full adder, okay? And I did that in Verilog too, okay? My first half adder is called U1. My second half adder is called U2. And by using these intermediary wires here, I have the intended, I create a circuit with the intended behavior here, okay? So my carry out is going to be the OR of F and D, and then the sum is going to be equal to the result of the intermediary wire E, okay? So it looks like I've completed this. The only thing that's left now is to create the test bench. Now, like I said before, you need to use this video to add comments to this code, otherwise you won't get credit for this, okay? So the last thing we need to do is give this a run and make sure that this full adder is working the way that we intended to do, okay? And the way we do that is, you already know this, we're going to create a test bench. So here we're on step 5 now. We're going to create the test bench. So hover your cursor over Lab3A, create new file, and name the new file full adder underscore tb.v. Full adder underscore tb.v. Enter comments, type the following code, enter comments explaining what the code does. Code with no comments gets no credit. Okay. So here's what we're gonna do. We're gonna say backtick time scale 1 nanosecond over 1 nanosecond. This sets up our clock. Now we're gonna say include our full adder.v. So that way this test bench has access to the modules that we created in this file. Okay. Next thing we're gonna do is that we're gonna define our test bench. We're gonna say module full adder underscore TB, which represents our test bench. Now, the way that we know that this is a test bench is because there's no open close parentheses with inputs and outputs, okay? If we had an open close parentheses with inputs and outputs, this would be a circuit, right? Like the kind that you see here. Now, the next thing we gotta do is indicate our inputs and outputs. So inputs are represented with reg, so I'm gonna say reg, A, B, and carry in. And then outputs are indicated by the keyword wire. So I'm gonna say wire sum carry out. Okay. And now we're going to create an instance of the full adder, okay? So full adder. So by doing this, I created an instance of this circuit here, okay? Now I need to give this circuit a name, so I'm just gonna call it UUT, which stands for unit under test, UUT, and we're gonna give it 3 inputs. The 3 inputs are gonna be the same as we indicated here. So A, comma, B, comma, carry in. And our outputs are going to be the sum and carry out. So sum carry out. Okay. Okay, so we're ready to begin now. So we're gonna say, so we're gonna need this initial begin and end here to start and stop our clock. So I'm gonna say initial begin. Okay. Now I'm gonna need to add the parameters dump file and dump vars so that after I run the thing, it'll save the waveforms into a file that I can look at later. So I'm going to say dump file full adder underscore tb.vcd. So I'm indicating to Verilog that this is what I want my VCD file to be named afterwards, okay? Now I'm going to also say dump vars 0, comma, full adder underscore tb. Okay. And now I'm going to start putting my inputs. Now, if you look in this code here, I actually have a shorthanded way of changing the inputs of these, okay? So let me show you what exactly it is I'm trying to do. So let me make a new slide here. Okay. And let me start from here. Swap these, and then I'll use a pen to indicate what I'm doing, okay? So instead of, so even though you could do this, you could say A equals 0, comma, B equals 0, comma, carry in equals 0. And then you can wait 20 nanoseconds before doing the next set. What I'm doing here is actually a short-handed way of setting my inputs. So as you remember, A, B, and carry in are my inputs, okay? So So this first line here on 16, this is actually equivalent to the Verilog code that I wrote here in this line, okay? But the reason why that I'm writing it like this is because the way that this shorthanded way works is that by putting A, B, and carry in open close squiggly brackets, this is the same as saying this is the way as saying, okay, these 3 1-bit binary numbers, I'm going to treat them as 1 3-bit binary number. So so that's the purpose of the squiggly brackets, right? And now over here, I said 3, comma, D0. So what 3, comma, D0 means is that I'm setting this equal to the 3 bits binary number that's equal to 0 in decimal, okay? So the 3-bit binary number that's equal to 0 in binary is equal to 0, 0, 0, okay? After that, I waited 20 nanoseconds, as you can see here. And then I set A, B, and carry in equal to the 3-bit binary number that's equal to the decimal value of 1. So as a result of this, since this is 0, 0, 0, I'm basically saying, hey, this first 0, set it equal to A. This second 0, set it equal to B. This third 0, set it equal to C, and carry in, okay? And then in the very next line, I said this. I said basically the same thing. A, B, carry in. And I said, hey, set this equal to the 3-bit binary number that's equal to the decimal value of 1. So the 3-bit binary number that's equal to the decimal value of 1, this is actually 0, 0, 1. So what that does is that it sets A equal to 0, B equal to 0, and then carry in is equal to 1. And I kept doing this, I kept incrementing this until I reached 7, okay? What does 7 represent? So, let me draw it here. So A, comma B, comma carry in is equal to the 3-bit binary number that's equal to the decimal value of 7. The decimal value 7 represented binary would be 1, 1, 1. So I'm saying set this A equal to 1, set this B equal to 1, and set carry in equal to 1. So by using this shorthanded notation in Verilog, I cover every combination of the 3 inputs A, B, and carry in, as you also see in the PowerPoint here. So I need to cover all of these, right? If you look at here, 0, 0, 0 is equal to the binary number, 3-bit binary number of 0. 0, 0, 1 is equal to the binary 3-bit binary decimal representation of 1. And then if this is 0, 1, 2, 3, 4, 5, 6, 7, by doing it this way, I cover all 8 of my tests, okay? And I'm waiting 20 nanoseconds in between each test, okay? So that's the way that this is working. So these are good comments to add into your code in case you don't know what the code's doing. So I'm gonna get out of here, discard. So I'm going to quickly type all that as well. So comma A, B, carry in 3, comma D0, and then pound 20. That means wait 20 nanoseconds. And now what I'm gonna do is I'm going to repeat this line a bunch of times. 1, 2, 3, 4, 5, 6, 7. And then I'll just change this to a 1, change this to a 2, change this to a 3, 4, 5, 6, 7. Okay? So this is a shorthanded way of setting your inputs, so you might find that useful in the future. Okay? Now the last thing I got to do is I have this display finished additions here. So what this does is that this will display in the terminal after it's completed doing all of these, okay? Alright, so now that that's done, I can finish my test bench by saying end module, and that should be good to go. So now I just need to see if this actually works. So I'm going to do this. I'm going to save everything. Save all. And now I'm going to press Control backtick on my Visual Studio Code, which will open my terminal. And now I'm going to run this command here in order to create my VCD file. So I'm going to say iverilog -o full adder _tb.vvp, and then I'm going to say full adder _tb.v. Okay, it looks like I have a syntax error on line 4. Let's see what that's about. Line 4. Oh, I accidentally said outputs instead of output. Let me fix that. Then I'll save everything again. Save all. Let's try this again. Okay, so this time it worked because I created my VVP file, okay? So now I just have to enter this command here, which will create my VCD file. So VVP full adder _tb.vvp. Okay, so you know it worked because we said finished additions here. So now I have my VCD file, okay? Now, let me move my head here. Okay, great. So now I'm going to see if this works by entering the command gtkWave. This opens gtkWave for me. And now I'm going to click this, File, Open New Tab. I'm going to choose my VCD file, Open. Now I'm going to click this. And now here are my 3 inputs and my 2 outputs, okay? Holding down Shift, I can select multiples of them. I can click Append. And now I have my waveforms here. In order to make sure that this is working correctly, I'm going to compare this to the truth table for the full adder that I have over here. So let's check and make sure that it's working the way we wanted it to. So let's see. When A, B, and C in are all 0, sum and carry out should all be 0. So let's see, A, B, C, okay. This is 0 and this is 0, so that checks out. Let's look at the next set. After 20 nanoseconds, this is my new set now. A, B, and C in are set equal to 0, 0, and 1 respectively. So 0, 0, 1. Sum is equal to 1, which it is. And then my carry out is equal to 0, which it is. So that checks out. After that, I have A, B, and C in being 0, 1, 0 respectively. That's this next set here. Sum is equal to 1 and carry out is equal to 0. Sum is equal to 1. Carry out is equal to 0. Okay, so that looks like it works. After that, when A, B, and C in are 0, 0, 0, 1, 1 respectively, my sum is 0 and my carry out is 1. Okay. My sum is 0 and my carry out is 1. So that works. Okay. After that, when A is 1, excuse me. When A, B, and C in is 1, 0, 0 respectively, the sum is 1 and the carry out is 0. Okay. So that works. When A, B, and C in is 1, 0, 1 respectively, the sum is 0 and the carry out is 0. So sum is 1 and the carry out is 0. Yep, that looks good. And then when A, B, and C in is 1, 0, 1 respectively, the sum is 0 and the carry out is 1. Sum is 0 and the carry out is 1. That checks out too. And then when A, B, and C in is 1, 1, 0 respectively, the sum is 0 and the C out is 1. So the sum is 0, the C out is 1. So that looks good. And then lastly, when A, B, and C in are all 1s, sum and C out should be 1. So 1, 1, 1, 1, 1. Yep. And it looks like it's working correctly. Okay. So if you can provide the code, for fulladder.v, fulladder.tb.v, run the commands to give you your waveforms, and then compare it to the truth table for the full adder here. You should get the full points for part A. Now, let's look over part B together, shall we? So, if your Lab3A folder is open, you can close it by selecting the folder and clicking File, Close. Create a new folder in your 4010 Labs directory, call it Lab3B. Open this folder in VS Code. Here's what you're going to do in part B. In part A, you use the diagrams in the PowerPoint to construct a half adder and a full adder. This time you'll use the diagrams in the same PowerPoint to construct a full subtractor, a half subtractor, and a full subtractor, okay? So I have the PowerPoint here. So here's where I start talking about the half subtractor and the full subtractor, okay? So this is the way that it works. Subtraction can be done in a similar manner using circuits, okay? Consider the truth table. We have two binary inputs, A and B, and we need to subtract A from B. We have two outputs, difference and borrow. Difference is a result of the subtracting B from A. Borrow is set to true if we need to borrow it from the preceding bit, okay? So, here is the truth table here. As you can see, it's done using an XOR gate, a NOT gate, and an AND gate. In fact, let me draw these here. So if you were trying to get these properties here, you would need to use an XOR gate for the difference. You would have to put a NOT gate in front of this AND gate, and that's what this dot here represents. And then you would have to use an AND gate here. Okay. So, okay. So after you create your half subtractor circuit, just like you did for the half adder circuit, you would need to arrange your circuits in a way that it can construct this full subtractor here. So this is the way you do it. So this circuit here would represent your first full subtractor, which you could probably call U1. This circuit here represents the other half subtractor, which I guess we'll just call U2. Two inputs will go into the first full subtractor. This outputs here will feed into there. This first output will feed into the first input of the U2, and then this BIN will feed as the second input for U2. The second output of U1 will feed into this OR gate, and then the second output of U2 will also feed into this OR gate, and then lastly, the first output of U2 will be our first output. So, and then the OR of these last two outputs will become the output of the whole circuit. Okay. So, in case any of this seems confusing, maybe I'll give you a head start for part B. So, here's what I'll do. Let me close this folder. I'll go here. I'll make a new folder called Lab3B. Yes. So if you were trying to create the full subtractor, so I'm going to make a full subtractor .v. And you know what? I think what I'll do is get you as far as making your half subtractor, okay? So the way that you would do it is you would say, well, let's look at the circuit. So we're gonna say module full subtractor, or excuse me, half subtractor. And we're gonna have two inputs, one called op1, op2, and we're gonna have two outputs, one called diff for difference, and then borrow. Okay. So we need to indicate that op1 and op2 are inputs, so we're gonna say input op1, comma op2. Now we'll say output diff, comma borrow. Okay. Now we need to set difference equal to the XOR of A and B. So diff. So the way we do that is using the caret symbol, op1 caret op2. And now we need to set the caret. All right. This is supposed to say borrow here. I don't know why it's not, but it's okay. And then borrow is going to be equal to the not of A, because as you can see here, there's a not gate right before it enters into the carry input. So the way we indicate that is using the exclamation point, op1, and now we have to AND the not of op1 with op2. The way we do that is using the ampersand, and we're going to say op2, and then say AND module. Oh, actually, I don't need these curly brackets. Okay, so here's your module for the half subtractor. I'm going to leave it to you to construct a full subtractor on your own. But to do that, it should be very easy. To make the full subtractor, you just have to follow this diagram, the same diagram here, where you have inputs going into U1, you have intermediary wires, and then you also have an OR gate here, okay? So if you have questions about part B, you can always ask me in my office hours. Like I said, I'm going to leave it to you to make that module for the full subtractor and the test bench for the full subtractor. But in order to do that, it should be almost exactly the same as the test bench for the full adder here. But like I said before, if you run into any difficulty, you can always ask me via email or see me in my office hours. So I think this is enough material to get you started. I hope you finish this lab, and I'll see you in the next video. Thank you.